From Earth, the sun looks like a static, glowing sphere, but close up, the surface is a churning landscape of ionized gas and shifting magnetic fields. To see how it actually works, we have to look past that glow. We're going to put on a magically protected suit and dive right in to navigate the specific layers hidden beneath the surface. You start by passing through the first physical boundary. It's a distinct layer that you'd cross in just about 400 kilometers. This outer layer is hot enough to make diamonds boil. Once you cross this line, the physical resistance of the sun begins to escalate. You are moving into regions where the physics of the environment become increasingly dense. This 400-kilometer crust is just the beginning. Its presence shows that the sun isn't a uniform ball of fire, but a series of distinct nested zones that each perform a different task. Below the surface layer, the environment shifts. You are now sinking into a massive, boiling ocean of plasma. This chart shows how convection works here. Ionized gas rises, cools at the surface, and then sinks back down like a giant churning pot. As you try to descend, you're fighting against these constant, violent upward currents of hot plasma. The temperature in this churning layer reaches 2 million degrees Celsius. This entire zone acts as a transport mechanism, physically carrying the heat generated in the deep interior up to the surface, where it can finally escape. Deeper down, the churning stops. The violent motion is replaced by a zone of extreme crushing density. In this layer, the material is so tightly packed that light particles, photons, can no longer travel in a straight line. This tracks a single photon's path. With so little space between atoms, the photon bounces randomly, like a ball in a high-speed ping-pong machine. That bouncing creates massive delay. It takes 170,000 years for light to escape this single layer. In the radiative zone, density is the primary obstacle. It turns the sun's own light into a prisoner, forcing it to fight for thousands of years just to move forward. After the long descent through the plasma and the light trap, you reach the center, the core. This is the hottest part of the journey, where the temperature hits 15 million degrees Celsius. This is where nuclear fusion happens. The immense pressure forces hydrogen atoms together until they smash into one another. They fuse to create helium, a process that releases the energy that powers the entire star and makes life on Earth possible. This energy begins a long journey outward, pushing back through the dense radiative zone and the churning convection layer. It eventually breaks through the surface and launches across the vacuum of space at the speed of light. When you feel the sun on your skin, you are feeling energy that was born in that 15 million degree core and spent 170,000 years fighting its way out of the sun's interior.